Happy New Year! 2023 was a big year in astronomy. So as we ring in the new year, or if you're in Scotland, announce it with cannon fire from Edinburgh Castle, I thought we'd look back at some of the bigger stories in astronomy in 2023, and then towards the end of this video, we'll look ahead to what might be coming in 2024 for astronomy. If you're new, hi, I'm Thomas, welcome to the channel. I'm a PhD student in astrophysics at Cardiff University. It's so great to have you here. Let's cast our minds back to one of the biggest news stories in 2023. The claim from the media that astronomers at the University of Cambridge had discovered evidence of alien life. Claims of finding alien life are nothing new in the media when it comes to astronomy. Anything that possibly, might, maybe, with about 15,000 caveats, could be to do with alien life gets latched onto by the media. Remember phosphine on Venus, anyone? But this one was different. What we had here was a paper from Medusadan and collaborators at the University of Cambridge who'd used JWST to study the atmosphere of an exoplanet called K2-18b. They did this using the James Webb Space Telescope and a technique called spectroscopy. While exoplanet K2-18b was passing in front of its star, the light from that star passed through its atmosphere, being absorbed by different atoms and molecules that make up that atmosphere, giving you different absorption lines at different wavelengths. But a combined spectrum showing the starlight and the absorption lines from the atmosphere isn't that useful. So they also took spectra of the star while the planet was not in front of it. By taking a spectrum of the star on its own and subtracting that from the combined spectrum, we got a spectrum for the atmosphere, and this could tell us what that atmosphere is made of. What they found was a very hydrogen-rich atmosphere surrounding a very large water ocean, something they've designated as a possible Haitian world, a portmanteau of hydrogen and ocean. This is really interesting and a really cool new classification of world that does not exist in our solar system. But what the media really latched onto was this figure. What we see here are a load of different lines relating to loads of different molecules. This shows how much each molecule absorbs. Now, there's really strong features from water, from carbon dioxide, and from methane. But what the media really grabbed onto was this purple line, relating to DMS, dimethyl sulphide. Now, DMS, or dimethyl sulphide, is a molecule that we know exists on Earth. DMS is produced in industrial processes, but it's also produced naturally. And the only natural way we know of to make it is using biological life. Most dimethyl sulphide on Earth is produced by phytoplankton in the oceans. This means that DMS is considered a biosignature, a sign that life exists somewhere. Now, that doesn't mean that there is life on K2-18b. We do not know this. What the researchers found was a possible detection. It's on the borderline of being statistically significant, maybe. It's really not a detection. The authors are really upfront with this. They need more data on this exoplanet before they can say if DMS is there or isn't. It's a really exciting possibility, but right now we just don't know. But moving on from exoplanets and JWST, let's talk about the little telescope that reached its 10th anniversary this year, Gaia. Gaia is a mission from the European Space Agency that has been producing boatloads of data over the last decade and honestly has revolutionized astronomy. Its primary mission is to do precision astrometry, looking at the positions and motions of stars, as well as taking some additional data. And honestly, we have never had data like Gaia's data. Over the course of its mission, it's already mapped about 1.8 billion objects. We've had 3 full data releases in the past 10 years, and in 2023, we didn't get data release 4, we got a focused product review. Now, a focused product release sounds, really boring, but essentially what it is, it's a small data release, this time focused on the Omega Centauri star cluster, where Gaia found over 500,000 new stars. Stars we didn't know about before. This was done using a really specialised engineering mode on Gaia that I suspect may now be informing future observations with the telescope, but Gaia just isn't slowing down. Now, we've had 3 data reviews, as I said, but I don't think we're going to be getting the data release 4 in 2024. It's going to be containing data that's really hard to do an early data release. So probably 2025 at least, maybe 2026. Now let's look at cosmology and specifically the crisis in cosmology. This has been going on for a few years now, where we have 2 different measures of the expansion of the universe that do not agree with each other at all. But 2023 decided to toss more fuel on the fire of crises in cosmology with this new paper from Labbe and collaborators. This paper suggested that JWST data showed 6 really massive galaxies in the early universe. Labbe and collaborators detected 6 galaxies with JWST in the early universe, 500 to 700 million years after the Big Bang, with stellar masses comparable to the Milky Way today, with one of them possibly being 10 times larger than that. They came to this conclusion through a process called photometry, so in sort of wide band passes of frequencies, they collected all of the light and used that to estimate the mass from a mass to light ratio. Now, if these observations are correct and the masses inferred from the amount of light collected are correct, then this causes us a bit of a problem for our best model of the universe, lambda CDM. CDM being cold dark matter. There is a paper that came out towards the end of this year that is yet to be peer reviewed from Tamron and collaborators, and they suggest that actually this might not be universe breaking, or at least universe model breaking. Now, this paper hasn't been peer reviewed yet. There hasn't been another scientist who's gone and checked their work. But they suggest that what the solution could be is that the early galaxies have a top-heavy IMF, that there are more massive stars than we assume there are. What we assume, and what everyone really assumes when they do these mass-to-light conversions, is that the early galaxies have a similar distribution of stars as the Milky Way, a similar proportion of massive stars, medium-sized stars, and low-mass stars. There isn't really any basis for this assumption, we just don't have a better estimate. So what Cameron and collaborators are suggesting is that these early galaxies have more massive stars. Massive stars produce disproportionately more light than low mass stars. Add a bit more mass, get a lot more light. This would allow these galaxies to appear as bright as a Milky Way type galaxy with fewer stars. What we really need is spectral data from JWST of these early galaxies so we can see, do these galaxies have this top-heavy IMF? Do they have more heavy stars? The other big piece of news that we got in astronomy this year came from the NANOGrav collaboration. Now, gravitational waves have been grabbing headlines for the past few years, ever since they were discovered back in 2015. Geez, that was 8 years ago. Now, all of these observations since 2015 have all basically used the same method. You've got 2 long arms with lasers bouncing back and forth between them. You look at how those lasers interfere at the base station, and you look for that characteristic chirping signal that we got from that original 2015 detection from LIGO. This is really good if you're looking at stellar mass black hole level masses, so colliding neutron stars, colliding black holes, that sort of thing. What they're not good for is looking for another theory of gravitational waves, which is that there is a gravitational wave background. This is going to be at much lower frequencies. We're talking nanohertz frequencies, where it takes about 1 billion seconds, or 31 years for one full sine wave oscillation. But this is what the NANOGrav collaboration have been studying. They've been doing this with a pulsar timing array, a vast array of pulsars across our galaxy. Now, a pulsar is just a spinning neutron star. It's got radiation firing out of its poles, so it sweeps around kind of like a lighthouse. These are timed incredibly precisely. They don't vary very much at all. So we can look for unusual variations in the pulses we get from these pulsars, and from that infer, do we have gravitational waves or do we have something else? Because a gravitational wave essentially stretches and squeezes space, or space-time. So by observing these very well timed pulsars, we can look for variations in that caused by a gravitational wave background. And that's what the big announcement was this year from the NANOGrav collaboration. After 15 years of data collection and processing, they announced that they had found this stochastic gravitational wave background. This was a huge result and a huge collaboration that went into producing it. Over 200 scientists. And there were some PhD students in this group, PhD students like me, that were in nursery when the first data was taken as part of this massive study. But that's enough about 2023. What might be coming in 2024? Now, I'm going to say there are a lot of caveats here. I don't know what's coming. These are kind of just my best educated guesses, but let's go through a few things. First off, that crisis in cosmology. I don't think we're going to get a full resolution to it. There's the whole Hubble tension thing that's still going to kick around. But as far as those early galaxies, we might get something. I don't know if there's already planned observations for these early galaxies with a spectrum, but we might get these observations in 2024. So maybe a resulting paper, but We'll see. Hopefully, we don't have to throw out Lambda CDM, but you know, it's on life support at the minute, so let's find a solution. If we do have to throw it out, that's really cool. We have to get a whole new model of the universe, but either way, we're going to find out new stuff. Speaking of JWST, let's talk about telescopes. So we already talked about Gaia. We're not going to get DR4 in 2024. We might get an early data release, but I think it's unlikely, having spoken to people who work with this data all the time. However, we are going to see more people digging into data from DR3 that came out in 2022, and particularly from this focused product release on Omega Centauri. The Euclid Space Telescope went up in 2023, and like Gaia, we're not going to get a data release in 2024. But we might get a few select images released. We already had some first science images. Euclid is going to be mapping the sky, about a third of the overall sky, looking at galaxies and trying to fill out our galaxy populations and trying to see more about how these galaxies evolve. So that's really exciting. I'm really excited for what's going to be coming from Euclid. But yeah, probably not a data release, probably just some select images. Then, of course, we have JWST. Currently, it's in its second year of operation, it's called Cycle 2, but this will come to an end in June. In the next few months, we will see which proposals have been accepted for Cycle 3, its third year of observations. If I had to guess, we're going to have a load of stuff about early galaxies, exoplanets, and probably a few things on star formation, but I'm not sure. I think most of what we're going to be probing is really deep, far away objects that are like really high redshift. It's what JWST is really designed for. We'll also hear a fair amount about upcoming telescopes. Specifically, I think the Vera-Rubin telescope, which I believe is due to come online in 2025. We're going to start seeing a lot of people talking about how they're going to be treating the data from that, producing mock data sets and running pipelines showing how we're going to be processing all of that amazing new data. The Vera-Rubin telescope is based in Chile, and it's going to be mapping at the southern sky with incredible detail, something we've not really been able to do before, testing our theories of dark matter, dark energy, looking for transients, so really like instantaneous objects like supernovae or gamma ray bursts. And although it's a survey telescope, it is going to look much deeper than most survey telescopes do, which only really go out to a couple of redshifts. The opportunities that this telescope is going to give us are just kind of mind-boggling to think about. Now let's think more about some of the other things we mentioned before. There's the DMS discovery. Now, I don't think we're going to get a resolution to this in 2024. I don't know if they've already been given more telescope time to observe this. I don't know if it's Cycle 2 or maybe it might end up being in Cycle 3. If it's in Cycle 2, we might get a preprint paper saying what they think they've found. But if the observations are in Cycle 3 for JWST, we're probably not going to get this paper until 2025 at the earliest. But we are definitely going to get more exoplanet spectra through 2024. There's going to be a lot more observations of this from JWST in Cycle 3, but there's already been more in Cycle 2. So exoplanet spectra is what JWST is designed for. It was one of the first things they showed us when we got those first images back in 2022. So now I want to think a little bit more about computing and simulations. There's going to be a big data release from the Auriga project. And this is a galaxy simulations project. It's actually what my work is based on. Now, a big public data release is due in December 2023, but I'm recording this in December 2023 and it hasn't showed up yet. So I suspect that may be coming in early 2024. I'm really excited for this because what we normally see with public data releases is people able to compare their simulations to existing simulations. It's happened with the Illustris project. You see a lot of Auriga stuff from people within the group who are comparing their Auriga simulations to Illustris simulations. And it'd be really cool to see Auriga stuff being compared to in the same way. And then the other big computational thing I think we're going to see in 2024 is a further proliferation of machine learning and artificial intelligence techniques in astronomy. We're already starting to see it, but I think these tools are going to become even more useful for us when we deal with bigger and bigger data. There's new telescopes coming online that are going to be producing petabytes of data, not the normal terabytes we're used to. I'm sure we're going to see more of this going forward. Hell, even I'm looking at using it for my own research. And then the other thing with AI is we're going to see more discussions about the use of ChatGPT and other generative AI tools in academia. I know these discussions are happening. I've been in some of them, and I know that there is active research going on into how it's used in academia. I don't think there's going to be a consensus on this in 2024. I think that generative AI is moving too fast for policymakers, and I worry that policymakers are going to get it wrong, but that's maybe a topic for another video. I don't have time for it today. All in all, I think 2024 is going to be a really big year in astronomy. There's going to be a lot of wide-ranging discoveries that are going to be so exciting. I also think we're going to see a big gearing up towards big telescopes coming in the next few years, like Vera Rubin, like Nancy Roman. There's going to be other big telescopes coming in the next few years as well, and then data from the likes of Euclid. But only time will tell if any of the stuff I've just said is right. It may be completely wrong, but I'm going to be interested to see how wrong I'm going to be. There's no way I've got everything right. Now, I hope you've had a really good winter break, or summer break if you're in the southern hemisphere. If this is your first time watching one of my videos, thank you for watching it all the way to the end. If you'd be so kind as to hit the like button and subscribe, then that would make my day. If you want to discuss any of the things I've talked about or predictions I've made, then you're more than welcome to comment down below, but I would actually suggest you come and join us on Discord. This is the hub of my whole community online. It's the hub of everything I do, and it's where people can go to talk about science, about astronomy, about the things I make, or just have a chat in general. The link is in the description below. I'd love to see so many more people joining us over there. And with that, thank you very much for watching. I'm really looking forward to what comes this year, both in astronomy and here on YouTube. Thank you again, and I'll see you in the next one.